So today we'll talk about variable mass flow problems. So very interesting, rocket science is what we'll discuss today. We'll have only one lecture on rocket science, that's how easy it is. So till now we have talked about situations where the mass of the system is constant, okay, or mass of whatever we are considering is constant. It's only the velocity that changes with time and position. But now we'll talk about situations where mass is flowing from some volume. So an example could be rockets. So in rockets what happens is, if you think of a rocket, there is some fuel inside it and some oxidizer, and there is a reaction that happens and gases rush out at large speeds related to the rocket, and the rocket gets a thrust in return and starts moving, accelerating. That is what happens in a rocket. So it's a variable mass flow problem in the sense that mass is getting change of the rocket with time. That is something that we have not discussed, so we learn how to deal with those problems. So it's a system of particles. In fact, we have infinite number of particles now, but the particles, if we take a volume, that is our rocket, its mass is changing with time. Other examples can be turbines, get power. So you should appreciate the fact that we have turbines of different types. They could be hydraulic turbines, they could be gas turbines, they could be turbines used in aircraft engines. So they're all used to convert mechanical power to electrical power. Okay, so that is what they're used for. Pumps, the other way around, they are used to convert electrical energy to mechanical energy, and that is what happens when it pumps a fluid, for example water, up some height. So these are typical examples that are very common of variable mass flow problems. To make things simple, we'll talk about systems which have a steady mass flow first, that is whatever is entering is whatever is leaving, and then we'll talk about variable mass flow problems where whatever is entering is not equal to whatever is leaving. And then again we'll simplify our, so we'll solve a lot of problems today. We'll simplify the discussion by starting with situations where the velocity of the system is constant, so it's not accelerating. We are ensuring that the system is not accelerating. So that is a simplified situation, and then we go to situations where the system is accelerating. So we will define a volume. I'll tell you what is the difference between volume and system. Till now we've been talking about system, the word system. So we'll say that there is a physical volume or an imaginary volume. That is our choice. Like you do in free body diagrams, you either choose a physical body and apply the net forces acting on it externally, or you take a part of it, an imaginary cut that you make, and then you find out the forces external to the body. Similarly, we'll talk about volumes. Sometimes we call them control volumes, but that doesn't matter. So we'll talk about volumes. They could be physical volumes, as in like the body of a rocket, or they could be imaginary volumes, as in like half a rocket. So you hypothetically slice it, and then you take the imaginary half and find the forces acting on that half. So this volume can be physical or imaginary. And then we have already used the word system. Now that's very important to differentiate between a volume and a system. System is a collection of mass particles. So till now we have said that when we deal with a collection of particles, we identify them from indices, from I going from 1 to n. So we have n particles. Now for an infinite number of particles, like a continuous system, like you have a rocket, we will still talk about a collection of masses. So if there is a gas that is leaving the rocket, then if you're talking about a system, that includes, let's say this is the system at time t, and at time t plus delta t for this rocket, there is also a gas that has left the rocket. So at time t plus delta t, my system will be all this. Whereas if I talk about a volume, so in this case my volume is under consideration is the rocket. So the volume still remains the red part, that is the rocket. So that's how we define things. There's nothing, there's no reason to fight these definitions. These are definitions. That is how we. So when I use the word volume, it should identify a volume. It does not change with time, although it can, but we'll keep problems simple. And system will consist of some identified particles. So if some particles enter the volume, they will not be a part of the system. It's only what we define the system at any given time. So in this case, the system was defined at time t. So at time t plus delta t, the system has increased in size because it includes particles which have left the volume. So we have to expand the boundary of the system to include all the particles that we started with. Okay. The reason is because Newton's second law does not work for volumes. That is a classic mistake we end up making in many situations. Newton's second law says the force acting on a particle is equal to its mass times acceleration, and the force acting on a system of particles is equal to the time rate change of the momentum of that system. Right? So we have to make sure we can still apply those laws in the way we have discussed them. So that is the reason we need to make sure our system definition is correct. I mean the way we are identifying the system is correct. So I'll give you an example and we'll develop the theory through an example. So this is a pipe elbow. So we see pipe bends in pipes all the time in plumbing. So this is an elbow that is used to change the direction of flow 90 degrees. The inlet area is different from outlet area. Some fluid is entering the pipe at a velocity of v in or a speed of v in. So velocity vector is perpendicular to the surface or it's along the normal vector to the area, and it's leaving out at a velocity v out. The density of the fluid when it enters is rho in, and when it leaves the elbow it is rho out. So the density of the fluid can change. M prime denotes the mass flow rate into the system. So we have M prime in. So in a unit time, how much mass of the fluid flows into the system, and M prime out denotes the mass flow rate out of the system. So in the first situation, in this example, we will take M prime in equals M prime out. So this is a steady flow situation. Steady flow means whatever enters leaves, nothing gets collected, no mass gets collected or depleted inside our volume. The volume is the red part. Now we have to define a system. So at time t, if we define our system, as containing all the particles inside the pipe. So there will be some at time t some fluid particles inside the pipe, and I also take some extra amount of fluid that is about to enter the pipe. So I am drawing a dotted line, differentiate between the volume and the So, the complete solid blue line is the system. So, it includes whatever is inside the pipe and an extra mass delta m about to enter the pipe. So, this is the definition of system. Okay. I do not need to write at time t because this is how I have defined the system. Incidentally, at time t, this is how it looks. There is some mass about to enter and some mass inside the pipe. Now, if I take a different time, this mass, this system will have a different boundary, because this mass about to enter. So, let us say this is at I should write, let us write at t, and at time t plus delta t, system boundary changes. So, I have defined it in such a way, I know what my delta t is, that now the system, we need one more color. After time delta t, all this mass has now entered the pipe, but some mass that was inside the pipe has left out. This is also delta m, because delta m mass entered, so delta m has to leave, because the mass inside the pipe has to be constant. It is a steady flow situation. The system still has the mass m plus delta m. Now, what are we solving for? What are we doing here? What happens is, if you had a pipe which was just kept on a floor, let us forget about gravity for now. Let us say the gravity force balances the normal reaction. The flow is in the plane that is normal to the gravity vector. So, in this plane, the flow, when it hits the pipe will have a tendency to accelerate. You have an intuition for that. So, we have to hold the pipe in place. So, we have to apply a force on the pipe so that the pipe stays stationary. So, our job is to find what are the forces we have to apply on the pipe to ensure that it stays stationary. Matter of definition, I told you system we choose. So, we decide what particles constitute the system. That was my choice. So, we will say some clamp force which has to be applied on this system so that it does not accelerate. So, we have to find out what the clamp force is, because when the water hits the pipe, it will move, right, in both directions. When the water direction changes, you will see that, I mean, if it was not intuitive, that is fine, we will see that from the equations. Since it is given that it is a steady flow situation, so m prime in is equal to m prime out, that is what this equation says. Mass flow rate is density times volume flow rate. So, density times volume flow rate is area times velocity. This I am sure you know from your thermodynamics. It is a collection of particles. So, we will apply Newton's second law, which is given as the force acting on this system of particles is the time rate change of the momentum of the system. This we have established. Let's see what the momentum is at time t plus delta t. The time t plus delta t, you should see the green envelope. Can we see the green envelope? For those sitting at the back and paying attention, can you see the green envelope here? Okay. So this momentum at time t plus delta t includes all the particles inside the pipe plus some extra particles which have moved out. So we will do a summation of mass times velocity of all the particles inside the volume plus an extra part. The extra part has a mass delta m and the velocity is V out. Now, if we look at time t, that is the blue envelope, that again includes all the particles inside the pipe, and it also includes some particles about to enter the pipe. So, for those particles inside the pipe, they will have the same velocity. Okay. It may not be the case, but we have taken a steady flow situation, so things do not change with time inside what is happening in the pipe. So, if you look at any point in the pipe and whatever particle is there, its velocity will be the same at all times at that point in space. That is called steady flow situations. If you have switched on the flow and the flow is still taking time to develop, that may be a different situation. But for a steady flow situation, we can say that this and these are the same. So, whatever is happening inside the pipe is the same situation. Plus we have a delta m about to enter. So, that is delta m times the velocity at the inlet. If we apply the limit delta t tending to 0, and that gives us delta m by delta t is nothing but the amount of mass entering in a given time, unit time. So, limit delta t tend to 0, that becomes, we will call it m prime because that is what we have been calling it. For this pipe flow situation, our time rate change of the momentum of the system is m prime times the difference between V out and V in. Very interesting. Let us analyze this. Now, there was a question, why is the pipe going to accelerate? Because the particles will hit the pipe. The particles have a momentum, so they will deliver the momentum, or they will change their momentum from this direction to this direction. So, they will end up providing a force on the pipe. That is the reason we need to hold the pipe. But in this final outcome, we don't have to analyze how the particles are interacting with the surface. All we need to know is what are the conditions at the inlet and the outlet. What is the velocity of the flow at inlet, what is the velocity of the flow at outlet, and what is the mass flow rate. All right, that's the usefulness of this expression, and this is for variable mass systems, in the sense that the mass is entering and leaving continuously. And this is equal to the sum of all the external forces acting on the system. Now, these forces will be physical forces. They could be, in this case, they could be some clamping force, as we have discussed. They could also be a surface force, in the sense that a force that is applied because of the pressure at the inlet and outlet, because we have taken a system of particles. So, whatever is outside it can apply force. So, if there is a water surface connecting with another water surface, there could be a force because of the pressure from outside. So, you have to consider all the forces that are external to the surface and then make it equal to this dP by dt that has details of mass flow rate and velocity difference at the inlet and outlet. So, this was force. Let us talk about the second dynamical equation, that is torque and linear momentum. So, linear momentum about O, a fixed point O at time t plus delta t. So, that includes all the particles inside the pipe plus some portion that is moved out of the pipe. So, delta m amount of mass has moved out. So, the linear momentum, the angular momentum about O, for that mass delta m moving out with the velocity v out is r out. R out is a vector from O to, let us say, this point. Now, we do not worry about the spatial differences as in the mass delta m, because delta m ultimately delta t will tend to 0. So, that spatial difference will tend to 0. So, we assume that things do not change over delta m. Delta m is a small mass. This is the second dynamical relation that relates our torque due to external forces, well, torque about O, with the time rate change of the angular momentum of the system. Now we solve a problem. So we have a fixed vane like a surface. There is a water stream coming towards the vane, and that vane simply deflects a water stream which has an open surface. So the job of the vane is to deflect the water surface by an angle theta. It is a smooth vane in the sense there is no friction on the surface. The water stream is open from the top. The mass, the density is rho for the fluid, that is given. The flow is entering with a speed of v. So our job is to find the force that we have to apply on the vane to ensure that the vane does not move. So in short, we have to find these two components. R and F. Is the problem clear? Now this is a variable this is a mass flow problem. We have to choose a volume and then apply the equation that we have just developed, which was this one, dP by dt is equal to m prime times V out minus V in. So let's write that will help us. Our choice of the volume that we take is the green one. The vane, the object, the physical solid object vane is taken inside the system. That does not matter. So what happens is the forces R and F now are outside our system. And now I keep talking about system and volume because now we have taken delta T tend to 0. So our volume and system are coincident now. Okay. Earlier delta M was there, but now since delta T tended to 0, so that collapsed to the volume. So I will keep the word, use the word system and volume now interchangeable in this problem discussion. Now if I had taken the system, the green part, only as encompassing the fluid that is flowing over the vane, then I will have to find out the interaction forces of the vane with the liquid. But I would want to find R and F, which are the forces applied on the solid object, that is the vane. So I take the vane inside my system.
That was my choice.
So this equation that we have has two components, one along x, one along y. So x is this direction and y is this direction. So let's find out, let's write this for both directions. In the x direction we write it as minus f equals m prime times v out, the x component of that, minus v in, the x component, now we know that it's a steady flow situation in the sense that whatever enters is whatever leaves. So we have m prime in equals m prime out. The density is constant, that's rho. So the density does not change between inlet and outlet. So we have rho times A, again A is the same area, the area of the fluid does not change. So rho times A times the magnitude of inlet velocity is rho times A times the magnitude of outlet velocity. So that gives us the outlet velocity also as V. So when we want to find out the x and y components of V out, that's simple now. The x component of V out is V cos theta. And m prime is rho times A times V, and then we have another V times cos theta minus 1, and I mean cos theta is less than 1 or equal to 1. So this we can write as rho A V squared times 1 minus cos theta. What happens to r when theta becomes 0? The vane is a flat vane. What happens to r? What happens to r? Yes. Is that intuitive? R was this force. What happens to F when theta becomes 0? F becomes 0 as well. Is that intuitive? It's a smooth pipe, there's no friction. If there was a friction, then we had to consider that, but for this situation, it's a smooth pipe. Okay. Now, what if I ask you, for the same situation, there's a stream from a fixed point of view, the stream's moving with v, and instead of having a fixed vane, I have a vane that now moves with the velocity of u away from the water, but u is less than v. So, the water will still hit the vane. So, let us call it part B of the problem. The vane moves with constant u towards right, but u is less than v. So, the water will still end up hitting the vane because vane is moving with a speed which is smaller than the speed of water. Can you find V and R now? Quite simple. Simply replace the V in expressions for F and R with V minus U. Because if you now take a frame which is moving with the vane, that is a Newtonian frame. That is an inertial frame. You analyze the problem from that frame and you will simply end up changing from V to V minus U, because that is the speed of water that the vane sees, or the frame that is moving with the vane sees. This is ideas of relative velocity, you already know that. In case you do not feel satisfied with what I have told you, you can analyze the problem from O as well, the fixed frame. Even then you will get the same thing, but then you will have to go through those steps of finding delta V x and delta V y, and then equate them to the forces, but analyze them from a fixed point O. Choice is yours, you can try it yourself. Another problem. So, we have a spacecraft that is moving through space with a constant velocity v. The spacecraft encounters dust particles that are approaching the spacecraft with a speed u. And the dust particles are approaching at a mass flow rate of dm by dt, that is given. So, in any given unit time, dm by dt amount of mass impacts the spacecraft and sticks to it. It is embedding, they embed themselves on the spacecraft. So at time t, the total mass of the spacecraft is capital M, is a function of time. Now as the particles embed on the spacecraft, the mass will change, but it's given to you that at time t, it's capital M. You have to find the external force required to ensure that the spacecraft moves with a constant velocity v. Whatever dust particle embeds on the spacecraft, you have to ensure what force has to be applied externally on the spacecraft so that it keeps moving uniformly with v vector. Now of course, that force will come from the thrust generated by the spacecraft itself, but that is a problem for Friday. But what you can assume that there is an imaginary hand that is can apply the force on the spacecraft so that it keeps moving uniformly with O. In the next lecture, we will figure out how that imaginary hand, the force, can be generated through thrust inside the spacecraft. But this is a constant velocity situation. There is no acceleration of the system. That is slightly more complicated. So for this situation, I request you to please think for a minute or two as to how you will approach this problem. You can either use the relation we developed, or you can also start from first principles by finding the momentum of the system. So you define a system, and then you take its momentum at time t plus delta t, and time t, take a difference, approach delta t tend to 0, and find the force F. I have given you the answer now. Now you can reverse engineer. You can take a delta m amount of mass that is about to hit the spacecraft, that is at time t plus the spacecraft mass, and then after delta t time, that mass has stuck to the spacecraft, and you also have the spacecraft and its own mass. These are the two situations. Now you can do momentum at time t plus delta t minus momentum at time t divided by delta t, and take the limit delta t tending to 0. My choice of system was the situation at time t on the left hand side, where you have the spacecraft moving with v plus an amount of delta m dust particles that are about to impact the spacecraft and get stuck to it, and these particles have a velocity of u. So the momentum becomes m, capital M times v times plus delta m times u. Now after time delta t, these particles, dust particles, now have stuck to the spacecraft, so now they are moving with v. Now if we take the difference, this term does not contribute anything. Divide by delta t, take the limit delta t tend to 0. This is your force, so that becomes dm by dt times v minus u. Now if u was 0, do we still have to apply a force? Dust particles are just appearing on the spacecraft without any speed because the mass of the system is increasing. Now you have to develop your own intuition here. But now you need a force because you need to accelerate that mass that has now got stuck to the surface as well, because it came with 0 speed. What if the dust particles came with a speed of came with a velocity of v? Do you have to apply any force? Because they already had a speed of v, they'll keep moving. There's no resistance as such, unless we model the resistance. But there was it's space. There's no resistance. So dust particles now very comfortably started flying with the spacecraft and then sat on them. That is okay. No speed required. So it's always good whenever you solve a problem, try to play around with the result. Try to think what happens if my u is equal to v. What if it's perpendicular to v? What if it's opposite to v? So that will help you develop intuition. The theory will simply tell you what equations to apply, but this will help you. And once in a while, try to use first principles rather than using a formula to reinforce the understanding of how you got those ideas, like we did here. We could have simply applied v minus u times dm by dt, but we tried to use first principles. On Friday, we will continue the discussion with a few more problems on how jet aircraft works in more detail, and then go to rockets. Thank you very much.